Right, so in this video I will describe binary search of the floor or ceiling in a sorted array with more repeating elements. So first of all, let's define some sorted array. It says nums is equal to 1, 3, 5, 7, 10. And let's say we have a target which is equal 8. So the 4 is the first element which is less or equal to our target. So in this case, the first element which is less or equal is 7. Our target right here. And the ceiling is the first element which is greater or equal than our target, which is 10 in this case. Ceiling and the 4. Okay. So our target is to come up with an algorithm that will find this 4 or ceiling indices in O log n time. So in this particular case, in order to solve this problem, I will be using a combination of binary search algorithm. If you don't know what binary search algorithm is and how it works, there is a video which I recorded which describes it in detail in one of my previous videos. So in binary search algorithm, what happens if we define lower left and right indices, and we constantly narrow down the search space by taking the middle element, which is equal to L plus R divided by 2. In this case it will be 2, so R will be 4, L initially will be 0, and we'll be moving by constantly dividing the remaining part of an array in 2 until the algorithm converges. So the difference between the implementation of algorithm which I recorded earlier is that in this particular case I will be using recursive calls. So let's define some recursive function. Let's call it def. Let's consider first for implementation. The ceiling will be pretty much same. So binary search for inner will take nums, it will take target, and it will take left and right. So let's assume this is our array nums, which is from 0 to n minus 1 indices, and we have L and right indices. So in this function we pass the nums array, we pass the target obviously, which lays somewhere, and we pass two left and right elements. So let's first look at the corner cases. So let's assume that if it is for operation, what happens initially, L will be equal to 0, and the very first call, if our target lays somewhere lower than a left foremost element, that means there is no element that is less or equal than our target. So in this case, if target is less or equal than the nums L, just need to return -1, because there is no answer. If from the other hand, the target is somewhere here. Initial r will be n minus 1. That means that the very last element will actually be our answer for the for operation. So in this case, nums are less or equal than target. So we just yeah, by the way, it's not equal here. It's less. So if it is less or equal the target, we return r. Okay, so what if it is not? That means that our target lays somewhere right here. So it's just like less than r, but it is greater or equal than L. So it is right here. We already took off this element. So if it is somewhere here, what we need to do, we just need again, so take the middle element, and we need to check if it is trivial case, where if nums m is equal to target. So if it is the case, what we do, we just return m. So if it is not the case, that means there are two possibilities. So if t is not equal to m element, that means that t actually either here or here. It's not here anymore, it's not here, it's not equal here, m's element, so it is somewhere between L and m. Okay, let's look closer. So let's say we have a bunch of elements. This is m's element, this is m's minus 1, this is L. So there are two actually cases. One is that our target lays here between the, it is equal or greater than m minus 1, but it is less than m. So if that's the case, our answer is this element right here, in case of for operation. If it's not the case, like this is the one check we need to do, and the second check we need to do is that so you just need to repeat the same search for this portion of an array. Okay, let's do it. So L if nums m is greater than t, so t less than nums m. Let me actually rewrite it. It's more kind of neat than when written this way, nums m. So in this case, we need to check first, like do some sanity check. So we check that L is less or equal than m minus 1, and our target is greater than or equal than m minus 1. So in this case, we return m minus 1, we return this guy. If it's not the case, we should repeat the same actually procedure for all elements starting from R to L, from m minus 1 to L. So in this case, we return a binary search f inner nums L m minus 1, and we need to put target right here. Okay, cool. So it's not the case. That means that, so we covered this part. Okay, so what happens if it's not the case? So that means that t is somewhere here. So again, that means that t is somewhere in this range. And there are two cases. First case is that t is less than m minus 1. In that case, the answer is m. So if t is here, it means it is either m or greater, but is less than m minus 1 element, so we need to return m. If it's not the case, then it is somewhere from m minus 1 to r. Okay, let's write it down. So else if we do sanity check that that m plus 1 is less or equal than r, and the target is less than nums m plus 1. In this case we return m. So otherwise we return binary search f inner nums target m plus 1 r, right? And we repeat the same search all again until it converges. Okay, so we need actually to call it like at least one time, and we need to have external function. Let's define it. Let's define it. So def binary search f external nums target. Initially, let's check for a trivial case, do some corner case check. If not nums, which means if it is either none or empty array, we just return -1. So, and we need to call this function at least once. Let's continue right here. So, and we call return binary search external f external binary search f internal nums target 0 and len nums -1, and that's it. So the algorithm of the ceiling is pretty much the same. The only difference will be in our initial corner cases checks, and a little bit difference here in this several checks. Okay, cool. And about them I will talk in one of the next videos.